lecture number 5. And let me remind you that last time we started our discussion of conservation laws for the whole system consisting of electromagnetic fields and charged particles. And we made use of Maxwell's equations in black color, but we also, as I kept on emphasizing, for calculational purposes, we include the magnetic terms in Maxwell's equations to give us generalized Maxwell's equations. And at the end of the calculation, we put the sources, the magnetic sources, rho, m, and jm being 0, so as to get back the use of Maxwell's equations. And it turns out that that is a nice mathematical trick. And because by putting in the green terms, the magnetic analog terms, we can enforce automatically the so-called symmetry under duality transmissions. You remember when under duality transmissions, E equals to the B equals to the minus E aside from the factors. And then we start considering the question of conservation of energy. And the end result, and we make use of these equations. We use the equations to replace the sources rho, m, jm, and j by means of the equations in terms of the fields. So the end result is just written in terms of the fields. And at that point, we put the sources in here. Of course, the sources already got them and put in terms of fields. Okay, so the end result is that we get an equation which looks remarkably like the conservation charge expression. Conservation charge is del rho by del T plus divergence of the current density. For the discussion of conservation of energy, we found out that this del by del T of the sum of energy densities. This term refers to the energy densities carried by the electromagnetic field, and this is the energy for the charged particles. And you remember that the energy density for the electromagnetic field is given by this: 1/2 epsilon naught E squared plus 1 mu naught B squared. And then, so this is a form of the total energy density, and that's the counterpart of charge density, and then plus the divergence of S. S is the so-called Poynting factor. It has the significance of energy flux, just as it plays the role of J, just as J is the flux of the charge. S is the flux of energy. And it's given by this expression. And notice right away, you should have noticed right away that both expressions, the energy density and the Poynting factor, are symmetrical under the duality transmission. Under duality transmissions, E equals to B equals to minus E. And the minus side is important, that takes care of this cos side. Because when you interchange E and B, there's a minus side. And this one, of course, also this term equal to this term, and vice versa. So that both the energy density carried by the electromagnetic field and the Poynting factor are invariant under duality transmissions. And in fact, it is this duality invariance under duality transmission that led us to put in these magnetic analog terms in the calculations also. All right? And then moving on, we talk about conservation of linear momentum. And since the rate change of linear momentum is force, so that we were left to consider the force, F, and we write that as the volume integral of force density. And Griffith, I think, used the notation of small f. I think in my notes I used the notation of script f. Anyway, so that is. And if you have not put in the magnetic analog terms, you will see that only these two terms appear. But we, for calculational purposes, put in these two terms coming from the magnetic terms. And this was obtained by replacing, substituting the sources by using Maxwell's equations in terms of the fields. So that everything now is in terms of E and B. The green part comes from the magnetic innermost term. And then, okay, you see that right away, okay, this term is, okay, and this term, okay, the other direct summation, this goes to that, and this goes to that. And okay, this goes to that, and this goes to this. So that, in fact, you can always use, okay, excuse me, direct symmetry to write down the green terms. Or, in fact, you can use direct transformation to check your calculations. Okay. For me, it's important because I tend to make some mistakes or forgot about a factor of half or 2 or things like this. All right? So, okay, let me repeat one more time. So, I put those terms there, okay, and then I put the source, and the source has been 0, but okay, there's no place. Okay, the magnetic sources are not there anymore. So there's nothing to put the 0 to be 0. But okay, for people who did not start with the whole thing, with the general Maxwell's equation, the green terms are not there. But then they said, in fact, I want to put a 0 here to go along with this, and put another 0 here to go along with this. And the way they figure out that this term is 0 because divergence of B, of course, is 0 without the green terms, the magnetic charge density. So they put in 0 in this form by hand. Of course, they said, okay, why not just twice of this, for example? And they said, no, I want to have symmetry between this term and that term. And that's the symmetry. Okay, the duality symmetry, duality transformation, which is automatically written down from our approach. So we do not have to guess. Again, they put in this in the conventional Maxwell, from the conventional Maxwell solutions, this is 0. So they put in the 0 in this form to go along with that one. And they pick this, again, so as to be symmetrical between the symmetry and the direct transmission between these 2 terms. Okay. So I hope that by now you appreciate the advantages, at least in doing calculations, of in fact putting in the magnetic analog terms. So magnetic sources may not exist in the universe. Well, I hope they do, so that we can understand the quantization of electrical charge. But anyway, even if they do not exist in the universe, they can be constructed in our mind so as to facilitate calculations in the real world. All right, so much for that. And last time, we ended the last lecture by noticing that these 2 terms, involving time derivatives, can be combined into this form. And then we look at the quadratic terms in E, which comes from this term, and that term. And for this triple cross product, we write down those 2 terms, and this, this. It's nothing but the sum of this and that. Now, let us start from here and combine these 2 terms. Namely that I can combine them into the form divergence of E is a vector, and so a vector is denoted by 1 arrow. Now, let me explain why this. What's the meaning of this one? This gradient operator, it operates on this E and this E. But when it acts on this E, it also starts with this E this time. So that when it acts on this E, you have divergence E multiplied by E, which is this term. When this gradient operator acts on this E, okay, it is okay, gradient operator x on E, and okay, on this E, then it dots okay, this E. So that's not true. All right. So it'd be nice, okay, if somehow we can have, okay, so we have dealt with del T terms already. Oh, I'm sorry. Dealt with del T, okay, terms already. And so we're looking for divergence terms. Okay. But this has the structure of divergence. Okay. And maybe I should, okay, for in case you're confused, name it as one. Notice that these two terms carry one index. It's a vector. This is a contracted vector, so it's scalar. Okay, so let's see. So that let's look for ask the question of the certain component of this object. So we're interested in the ith component. I can be x or y or z. What's that? That would be, let me use, okay, that would be del j e j e I. Namely that, okay, this index for the gradient is a vector, it carries one index. It started with this. The jth component of this vector, and this is another e, which del j will add on and carries the index on. Here, jump is j is a repeating index, so we are using the Einstein summation convention. So sum over 1 to 3 already. That's the meaning. Okay. All right. Now, as I was saying, it would be nice to have this term also put in the form of divergence or something. But you said, there's no divergence, it's gradient. Well, if there's no divergence, we do something, okay, to make it look like divergence. So, then we consider, gradient of E dot E. And what is that? I'm going to write the gradient, which is a vector, as follows. Gradient vector dot with a unit that which carries two indices. So here's two. So that since it carries two indices, so I have to ask what is the, for example, ith component of this object, and which this object is called the unit at so that the ith, it carries two indices, say the ith component of this unit data is nothing but the conical Taylor function. All right. So this index carried by gradient data with the ith index carried by 1, so that the whole thing has one index left. So it's a vector. So this like this vector. So I can write this down. So this is nothing but del I delta I j. This one is. And sum over I understood. This dot here, this scalar product, is carried out by contracting the two with the same indices. So that's what we mean. So that we can write this gradient operator as the scalar product of the gradient operator and this unit dialectic whose components are just given by the Kronecker delta function. So in fact, the unit dialectic can be thought of as a 3 by 3 matrix, and with one a non-diagonal and 0 for the off-diagonal elements. All right? So that we have, can we write this as this is a minus divergent dot unit dialectic times E squared over 2. All right? Let us now figure out this term and this term. Those are constructed terms in E. Done. Results here. Of course, we can similarly work on the construct B terms. This term and that term. Oh, wait, this term, that term. In fact, you don't have to do the calculations. We have the calculations for the electric part already. For the magnetic part, we just have to use duality transformation to write it down. But of course, if you are conscientious, you should look it out first, then check by if you have made a mistake or not by appealing to symmetry under the duality transformation. But anyway, so plus conjugate terms in E and B would be this, and write that down. Okay, so that's that's one not. Let me see. Divergence, right? So there can be combined to be the form divergence of epsilon naught E, which is this term, and then a minus divergence of and that is an epsilon naught there, so it's 1/2 of epsilon naught E squared. Now, we can add in the magnetic terms, as you see. Under duality transformation, this goes into mu1 B, and under duality transformation, black pen. 1/2 of this, plus 1 of mu1 B. Well, I should use green color. 1 over mu B squared. So that what are inside the square bracket are terms. Oh, forget about the one thing. The unit dialectic. Sorry. 1/2. And then there is that unit dialectic. And we see right away that these two terms combine together before the energy density carried by the electromagnetic field. So I can replace that star this is this I U, E, E. And what's inside the bracket? Sometimes is it's a tensor, carries two indices or diagonal. This whole thing is denoted by T, two arrows, since it carries two indices. It's diagonal. And it's, some people use minus T for this, but I think Griffiths used plus T here. And this is known as the Maxwell stress tensor. It's a tensor, two indices. All right. So then now we can copy everything and write down. I think I'm done with this. Oh, okay. The force density is equal to this term. Just minus del by del T written on this. And this combination is from not E cross B. Since F is force density, so that is equal to minus rate change with the time of course, momentum density. Just momentum density carried by electromagnetism. And this is defined by the momentum density, P sub Pb. And then, what else? Then plus divergence of this Maxwell stress tensor. All right. So that again, you have encountered the two groups of terms. One involves del by del T, the other one involving divergence. So the same kind of structure as in the expression for conservation of charge. That's good. Because here P plays the role of rho. This T, the stress tensor plays the role of J. See, rho is a scalar. Now it's played by a vector. J is the vector. Now it's played by a double vector, which is attached with the arrows. Okay, and you know we should notice also something, namely that we have encountered this cross product before, E equals B, where in the expression for the Poynting vector, so that in fact the linear momentum density is related to the Poynting vector by, let's see, so multiplied by epsilon naught is there, and mu naught. Let me see if this is true. Mu naught calculate the left mu with epsilon naught, correct. So that, in fact, the momentum, linear momentum density is, aside from a constant factor, is given by the Poynting vector. We'll come back to this to see what's the meaning of that in a very quantitative way. All right? So now let's go back to the total force, which is the volume of the force density. So then obviously is given by minus the volume integral of this. So this is, I can write that as d by dt volume integral of P is this. So it's epsilon naught mu naught vector. I mean the Poynting vector. Have I made the sign correctly? Yes. Minus put this time derivative outside the polynomial side, this polynomial of PP, is that correct? And then we have the polynomial of the divergence of the stress tensor. Again, we now make use of Gauss law to write down the polynomial of the divergence as an area integral surrounding the surface of the stress tensor. We can check that the left hand side is a vector. On the right hand side, there are two terms. This is vector, and this. A vector dot with a double vector that gives you a vector. By the way, I should also have pointed out that this Maxwell stress tensor, as you can tell, is symmetrical, namely that you can write down the components of this tensor, its characteristics. In this, for this expression, for example, the ij component is given by, if not, ei bj. This bi bj. This is given by, the ij is given by this, the delta ij, the Kronecker delta function. So that this is a symmetrical tensor, a two tensor with two indices. It is equal to Tji. So it does not matter whether you write this go as dA dot T or T dot dA. See? Because of the fact that T is symmetrical. All right? So this is F. In integral form, this is good. This expression of conservation linear momentum, or this in the differential form. Now, for the static case, this term is not there for static cases. This term is not there. So that the force is just equal to the area integral of the stress tensor. So in component form, the ith component of F is equal to dA, well, let me write this as T dot dA. So it's given by Tij dAg. The dot index is now provided by having the repeating indices, contracting these two quantities. And just obtain Tij. Of course, we have the physical significance of force per unit area. And this is force per unit area. And Tij is, force, the ith component of the force per unit area, acting on a surface element oriented in a j direction. That's the meaning. The diagonal terms of the stress tensor, and this nothing but the pressure. Force per unit area is pressure. Have the dimension of pressure. And for the off-diagonal elements, those components are known as shears. And let me give one example. very, very quickly. I think it would be instructive. So that now, let me. So this is the expression for the stress tensor. Let me quickly go over an example which illustrates, hopefully, the usefulness of introducing the stress tensor. Let's consider example. A spherical crystal or something, a sphere, with charge Q to the charge Q. Let's divide this sphere, uniform distributed. Let's divide this sphere into two hemispheres. So this northern hemisphere will be this. With a diagonal disk. So the red part is the northern hemisphere. In this example, let's calculate what's the force acting on the northern hemisphere. All right? So we can now make use of that result. So the F, the force, can be written as the area integral over the northern hemisphere. Northern hemisphere with the integral given by the stress tensor. And the stress tensor for this case is very simple. Namely that this stress tensor for this case is given by here epsilon naught B0, so that we're left with this term and this term is epsilon, so minus the unit dialectic of 1/2 of epsilon naught E squared. We're supposed to do the surface integral over the surface, for the northern hemisphere. So there are two surfaces. One is the ball. So consider integral over the ball and the diagonal disk. I would go over the calculation only very briefly in order to save time. Just indicate how the calculations can be done. All right. For the ball. First of all, let's because implicitly we have already used this as the z-axis, this x and y axis. So that disk lies on the y plane. On the ball, R is just the radius of the sphere, and by obviously this problem has symmetry, namely symmetrical around the z-axis, so that obviously F only can have the z component, non-vanishing z component. So that you say f is equal to f times z hat. So that where f, of course, is f dot with z hat, the z component f. So that we only have, in fact, to the following, namely that we only need to do this. All right? Let's see. For the ball, dA is on this ball. dA is given by dA, which is big R squared times sine theta, d theta, d phi, times in the radial direction. And we're only interested in the z component of this thing, so that we're interested in f, the z component. That would be z dot this thing. Okay, so let me in fact go back to write this as t dot d interchange the two, because we can do that because t is symmetrical. So the t and dot dA that. But dA is in the direction of radial. First, r hat dA. So I have t dot that and then z dot that. T is dotted to the left by z, and dotted to the right with the radial vector r. And what is t? T is given here. Okay, so this is nothing but z, this term is epsilon naught, z dot e, z dot e, and then this e, dot r. Anything else? dA is outside. And then this term is minus, it's the unidatic with z dot unidatic dot r hat. Of course, unidatic looks like just one. So this is nothing but z dot r hat. So that I have z dot r hat. There's the epsilon naught. I can pour epsilon naught, in fact. On this. And then minus there's a 1/2 factor of e squared. That's it. I've dotted z on the left and r on the right. So it's that. But e, on the northern hemisphere is pointing, radially out. So e is e r hat on the pole. All right. So this is nothing but length of e times z hat dot r hat, and this is another z. And this one, e dot r hat. E is already radial, so that dot can be the magnitude e. So the whole thing is very simple. Given by z dot r hat. Z hat is that direction, r is this one. So that's between them is angle theta. So that multiply by cosine theta and this term also has E on top of it. And so then we have E squared, and E squared can become and this is 1 times something minus 1/2. So it's 1/2. And you can work out the magnitude of E on the surface. So then after that, you do the integration over the northern hemisphere. Then you're done. Half already. For the second half, namely that we have to still calculate the area integral over the equatorial disk. Oh, that's diagonal, equatorial, that's one. And just very briefly mention this part of the calculation. So on the equatorial disk, the azimuth angle is 90 degrees. And this surface, the disk, dA for this disk points down. So dA is equal to magnitude times k z hat. Where dA here, we can use polar coordinates for this. So it will be r dr d theta. But d PHYS. And on this equatorial disk, you can work out the electric field E. And then again, you know that we are only interested in the Z component of this force, so that you can do a calculation similar, in a way similar to what we have done. Just project out the Z component. And this part of the calculation is in fact simpler because in E along on this equatorial surface points in fact on the plane. I'll put that out. So that is R on the plane. So on the plane, on the equatorial plane, this is R hat. R hat. We are interested in the Z component only, so project out the Z. The Z. So, the part involving, this term in the stress tensor, would be 0. The only non-linear contribution coming from this term. So let me finish the exercise for you to finish up the calculations for this example. All right. Having said that, I have no use for this anymore, so I can erase this. And how much do I want to save for the Okay, so we are done with the discussion on the conservation of linear momentum. And in fact, what we should do next is to derive the expression for conservation of angular momentum. But things got complicated, and we don't want to use time for that. We'll instead just consider an example. So then now we see that electromagnetic field carried energy carries linear momentum, and you expect that it would carry also angular momentum. So the angular momentum, we use script L to stand for that. That would be given by that's the moment of the linear momentum. We will discuss an example using this angular momentum quantity carried by the geometric field, and showed that there indeed is conservation of angular momentum for the whole system. So the geometric field carry energy, linear momentum, and angular momentum. All right. So let me use this on the blackboard. I can erase on this now. Oh, before I do that, I think I said it, but then I almost forgot. Namely that I pointed out that the linear momentum carried by the geometric field is related to the energy flux. So let us examine this very quickly, the property. So we have linear momentum P is equal to epsilon naught mu naught. Epsilon mu naught, in fact, is there. In fact, has the value of 1 over speed of light in vacuum squared. S is energy flux. Energy flux, of course, is just energy times velocity, some kind of flux. And this linear momentum, of course, has the meaning of linear momentum is nothing but mass times velocity. So energy, let me denote by E, and mass is M. So this is divided by c squared. Velocity cancel. So if I put c squared to the other side, then I have E equals mc squared. Einstein's famous equation, which we will derive in the last part of this course when we talk about special relativity. It's just key that automatically this kind of relations comes up. It's no surprise, in fact, it's a matter of dimensional analysis. But the fact is that in fact it comes out automatically. So everything we're doing is consistent with special relativity. That's why I'm trying to tell you. All right. So let's discuss the conservation of angular momentum with an example. And we need to use many different kinds of I think we have enough. Let's say that we have a solenoid. In red color. So current going through. Let's say that n turns per unit length carries current I. And it has radius R. It extends all the way along solenoid. And coaxial with this solenoid are two cylindrical shells, one inside the solenoid and one outside. And for the one inside, let me use green color. So this is also a very long one. This is cylindrical shell. It carries charge positive, distributed uniformly, on the shell. And this cylinder has radius small a, It's a long cylinder, cylindrical shape. And then the other cylinder, in blue, is lies outside the solenoid. So I draw big. It's a long one. So it expands alpha. It has radius B. So in this example, B is greater than R is greater than A. And we will draw the z-axis. And on the outer cylindrical shell, let's say that there's a uniform distribution of charge, and with total charge then minus Q. And let me draw the whole thing from the point of view of someone looking down. Looking down. Then that person will see circles. So this there is this small green circle, and then there is this bigger red circle, and then there is this blue circle, and this is the z-axis. Now, let me tell you what the problem is. Namely that, there's a current I running around the solenoid. But that current is gradually reduced to zero. As the current is being reduced, if you do an experiment, you'll find out that the two cylindrical shells will start rotating in opposite directions. It turns out. And the question is, why are they rotating? As if they have certain angular momentum. And the question is, where does that angular momentum, the angular momentum for the two cylinders come from? And we are supposed to show the conservation of angular momentum, namely the angular momentum for the time when I is on, compared to the total angular momentum with later time when the current is totally switched off. Well, where does the angular momentum come from? Initially, of course, it comes from the fact that there's a current I going around the solenoid, so that in fact it will create it will create a magnetic field B inside this solenoid. So B coming up. So uniformity. But we also notice that this charge, positive charge on the green circle and minus Q on the outer circle, so that there will be an electric field pointed radially out. So what's this blue, yeah. So that there would be the electric field going from the post direction towards this. E, of course, is pointed radially out. And for this problem, obviously, we should use cylindrical coordinate system. So Z points up. R goes this way, radially out. And differential. The smooth angle is phi. So this is phi. It's an orthogonal frame. They are all orthogonal to each other. All right. So that B, of course, goes up. So it's along the z hat direction. And E, of course, points along radial direction. So E is radial out. E is E times the radial out direction. E. And E is non-zero, only inside in the region between the green and this green. The region between the two solenoids. Radial out. All right, so that in the region between the green circle, which is the inner solenoid, and the solenoid, in this region, both magnetic field B and electric field are non-zero. So in this region, the green region. All right? Both E and B goes up, and this, I'm sorry, E is only a radial component and non-zero. In this part, non-zero in region between small cylinder and the solenoid. All right. Now we can do the calculations on this side of the paper. Okay, this one is. Choose dirty. Okay, since both E and B are non-zero in the region, the green shaded region between the small cylinder shell and the solenoid. So in that region, both E and B are non-zero, so that obviously there is a non-zero. E is non-zero, B is non-zero, so the cross product is non-zero, so that P is non-zero in the region. So P, E, B is non-zero. And let's calculate what it is. P and P, E, B in the green shaded region is equal to epsilon naught E plus P. Obviously, you can calculate what the electric field is. It's simple. All you have to do is to draw a Gaussian surface. And so the one thing is that this goes, this is radial out E, times, oh, it's here already. Go ahead. And this can be worked out easily. And if it's an exercise, you do it. So this is equal to epsilon naught E, and then the vector index is curved by E is radial out R. Cos B, B of course is along the Z direction. And it's easy. B is nothing but the number of turns per unit length that mu naught times the current I. Anyway, so times B is B magnitude times Z hat. And look what's R hat? Cos Z hat. R hat, cos Z hat is pointed opposite to phi hat. It's minus phi hat. So this is equal to minus epsilon naught E phi hat. In the green shaded region. And now I'm interested to consider the angular momentum density carried by the instrumental field. That's given by R. What's that? And so that the angular momentum density is given by R cross P, and of course it's given, it's equal to, this, let's see, minus E, epsilon naught E, B, times R hat cross phi hat. What is R hat cross phi hat? R hat is this, cross phi hat is points along Z hat. And you can work out this combination, and you can tell right away that in fact in E there is a factor of 1 over R, so that will cancel this 1 over R very nicely. So that in fact this whole thing is a constant. So that inside the shaded green region, name it the region between the inner cylindrical shell and the solenoid, there will be a non-zero angular momentum density pointing along the Z direction, and the magnitude being constant. So that to work out its total angular momentum, all you have to do is do a volume integral. And since the angular momentum density is a constant type this direction, so that in fact this integration is easy. It's nothing but the volume between in the green shaded region. So this can be done very nicely. So that this is equal something along the Z direction. So when the current I is going on, there is an angular momentum carried by the field. All right? But of course, as the current is being reduced, then the angular momentum goes away because the magnetic B goes to 0. So that from non-zero angular momentum carried by the field goes down to 0 angular momentum goes carried by the field. But where does the angular momentum originally carried by the field? Gone. Well, it's not gone. It's conserved. In fact, we're supposed to show that. In fact, that shows up by the turning around of the two cylindrical shells. and we're supposed to show the, in fact, the total angular momentum to start with, when the currents is not, before the currents reduced, compared the total angular momentum carried by the two cylindrical shells after the current is completely reduced to zero, they match. So that's conservation of angular momentum. The first half is simple. Now it's the second half to show that the conservation of angular momentum is conserved. It's the hard one. And the question is, so the angular momentum eventually is being carried by the two cylindrical shells. But where do they get the angular momentum? Angular momentum, as you remember, has this property. Namely that, you remember, something called torque. Then we use the notation N. Torque is the moment, the rate change of angular momentum. Well, so the angular momentum is the time integral of torque. So let's find out what's the angular momentum carried by these two cylindrical shells. All right. To start with, we know that these two cylindrical shells carry charge. So that if there's an electric field E acting on those two shells, then potentially it will contribute to the torque. So N is given by the moment of force. The force is charge times the electric field E. One torque for each of the two cylinders. All right? So there's got to be electric field E somewhere, such that when you cross with the radial component, it's non-zero. Now you said, did we have an electric field already? Yes. But the electric field E is along the radial direction. So when you cross it with R, it's zero. So in fact, we need another electrical field E, such that cross product of it would not be zero. All right? How do we get that? Well, you remember now the important lesson that you should learn is that, as the current spin reduced, the magnetic B and also the flux is also accordingly, correspondingly reduced. So we have a change in flux and a change in magnetic field B. A change in magnetic field B, of course, induces an E. So that's the E that we should look for. All right? So that B, we know what it is. Then we can work out what is phi as a function of the current I. B is along the radial arc. Okay? So that, if you now make use of, Faraday's law, take, the area integral on both sides, and then the left hand side would be written by means of Stokes theorem as line integral of the E. So E, with Z pointed up, E would be pointed radially, pointed along the phi direction, circumferentially. So that in fact we do have an E composed of two parts, the original one along the radial direction, and then now along the direction, circumferential direction. This is caused by a changing magnetic field. And in the phi direction, R direction, cos phi direction, what's that? R cos phi, it's along the z direction. Aha! So you see along the direction that we expect it to be, because that's the direction we have the angle, the original angular momentum is non-zero along the z direction. So that works out. So I will leave it as an exercise for you to work out the flux. So as to calculate the circumferential component of the electric field E. Once that you have that, then you have you can calculate the torque acting the torque on the two cylinders. And once you have the torque expression, then you can integrate over time. From the time when the current was on to the time when current is switched off. Or from the case that the current is I to when the current is zero. Do the calculations for both cylinders. Then you will find the angular momentum. You know the torque on both cylinders. The tandem group give you the angular momentum carried by those two cylinders. Add them up. And the challenge is to show that in fact this is in fact exactly equal to the total angular momentum carried by the field before the current is turned off. So this demonstrates conservation of angular momentum. Oh, my goodness. I've spent some time on this. Okay. Cannot believe it. Time goes by so fast. Okay, so much for conservation or discussion on conservation laws. Now, in the remaining 5 to 10 minutes, let me start on a certain topic, which, in hindsight, I should have already taken care of when we talk about inductance. But at that time, I was afraid that we may not have enough time to do it, so that's why I postponed it. But now it looks like that, in fact, we can afford the time to do it. And I think it's useful enough to merge, so that time well spent to cover that topic. Let's talk about energy in magnetic field. You must have done this, energy in electric fields, last semester. And now let's talk about energy in magnetic field. And start with, let's consider, consider a certain circuit, and let's say that it has a current I running around it. And let's start with the question, how much energy is necessary to have the current I running around the circuit? Okay, well, you have to remember that, it takes energy, it takes work to get the current started, to get the current going. And let's ask the question, what is the amount of work? Let me stop here. To have one unit charge go around the whole circuit. Well, you remember, that would be the work, is energy. So there's dl, okay, that was for a unit charge, so that was a certain force for 1 unit charge. That would be the amount of work to carry, okay, to have one charge, one unit charge go around, okay, the circuit once. That's the amount of work. But just you remember, it's nothing but, okay, the EMF. So that the amount of work, okay, to have a current, amount of current, okay, dq going around would be dq, okay, is equal to, okay, the amount of work that you have to spend to have 1 unit current going around is, okay, the EMF. Is that. Except that, okay, you are doing the work against the back EMF. So in fact, there's a minus sign. And if we are interested in the rate of the amount of work that we have to do, we have a dt. dq over dt is the rate change of the current going around it. It's nothing but current. And okay, the EMF, you remember, is minus d phi by dt, the flux loop. And also for circuit, okay, phi is equal to, okay, the self-inductance times current. So that the EMF is equal to minus L di by dt. So that the rate of work being done on the circuit, okay, where the current, okay, I is given by minus is plus, so it's L, there's an I here already, then di by dt. This is dw by dt. So that the amount of work that you need to put in, or the amount of energy that you have to spend to get the current stuff from 0 to I is given by this inequality over the time. Okay, so this is W is equal to L. I is inside. So that we can divide, multiply out the d by dt. So this goes from the current 0 to the current I. Okay. And this is so 1/2 I squared. So the amount of work that one has to do to get the current in that circuit start from 0 to the I is that much. That's one form for the expression of, and of course this amount of energy would, can be sort of being stored in the system. So that's why it's energy in the movement. All right, and now let me continue. So let me write W as 1/2 of I L I. And what is Li? That's interesting. And I'll just erase it. Flux is Li. Okay? So that Li is flux. Flux is the area integral of magnetic field B. And magnetic field B can be written as the curve A. The area integral of curve, okay, of course, Stokes theorem says that it is the line integral of the A. All right. So that I can write this W as 1/2 I times Li. Li is phi. which is this. So line integral of A. Of course, okay, the dot product between the line element directly and I. Of course, we can put this vector on L to be on I, since they're in the same direction. So I can write this as 1/2 dl, okay, I dot A. That's another form of W, the energy stored in the system. And in this form, form is for a circuit involving line integral. One can easily generalize to the case where the current is not a line, but it's a volume current, for example, or surface current. So that, now I'm done with this. So then let me generalize this to 1/2 volume integral of, I is replaced by J by A. The next thing we should do is to do something that we did when we talk about conservation laws. Namely, replace the source by the electromagnetic field by making use of Maxwell's equations. What is that? Well, that is equal to, aside from this factor, curve B. And this term is not there because it does not change the electric field in the system. So that I have J is nothing but 1/μ0 curve of B. So this is equal to 1/2 integral, there's the μ0 there, of A dot curve B. For this expression, it's volume integral involving the current, this is of A. So this suffices to do the integration of the volume where J is non-zero. But of course, it doesn't help to integrate over a larger volume. The extra space to include space where J is 0, because then that only adds 0 to what you have. So you can make the volume integral to be larger than this. So volume integral larger than the direction where J is not 0 will work as well. All right. So now we have this, and let me see. So this can be written in a nice form, namely that it is the divergence of A cross B. Let me see if that's correct. So that this acts on both A and B, and so this will be B, this would have a term, B dot of A minus, in a moment, A dot curve B. So there will be two terms. So this, integral is given by this. And sorry, this term is here. So this term can be replaced by this minus that. So B dot curve A is B itself. Minus divergence of A cross B. This is the integrand, can be written in this, in terms of these two terms. and let's continue the discussion the next time. Thank you.